So the impulse and the delta function transformation. An impulse function or an impulse concept in general is a force that is extremely large applied over an extremely short period of time. So for any positive number epsilon, we can say that the pulse is delta epsilon and can be defined in the following form. So we have delta epsilon equals to 1 over epsilon multiplied by a function h of t minus h of t minus epsilon. So let's say we have here an x and y axis. This is representing the t. So we have an impulse happened in here with the magnitude. Let's see, we have an impulse with a magnitude of 1 over epsilon for a duration of time, let's call it epsilon, and this will represent the delta of epsilon, which is the impulse in this case, in terms of t. So this is the duration, and this is the magnitude, and this is the impulse function. Okay, now the Laplace table have a transformation between the f of t and f of s for the delta function can be shown in here. So we have the delta function over here. So delta of t minus a, if you want to take the Laplace transformation for this value, which is known as the delta function transformation, and this function sometimes called the Dirac Delta function. This function is being invented or discovered by the Nobel laureate Paul Dirac, and this equation is called after his name based on his it was a result of his work, obviously. So the Laplace transformation for this function equals minus a multiplied by s. And it's good to know on the side that the Laplace transformation of delta of t equals 1. Just good to know that. But now we're focusing here. If we have delta t minus certain constant a, what would be the Laplace transformation for that? Alright, let's take an example and try to see how we're gonna solve it if we have a Dirac delta function equation in it. We have an example in here. Y double prime plus 2 multiplied by y prime plus 2 multiplied by y equals delta function delta of t minus 3. Initial value conditions y of 0 equals to y prime of 0 equals to 0. Doing the Laplace transformation, as we learned previously, we can have in here for the y double prime s squared multiplied by y of s multiplied by 2s multiplied by y of s plus 2 multiplied by y of s equals the Laplace transformation for delta of t minus 3 is e to the power of a, which is 3, to the power of minus a multiplied by s. In this case, minus 3 multiplied by s. Okay, solving both sides of the equation, we're trying to find the y of s. After doing a simple math and simplification, you can get your y of s to be equal to 1 over s squared plus 2s plus 2 multiplied by e to the power of minus 3s. And this can be simplified in the following form: 1 over s plus 1 all squared plus 1 still multiplied by the term e to the power of minus 3s. Okay, something to mention. So since the Laplace transformation for 1 over s plus 1 squared plus 1 alone, without the Dirac transformation term, without this term, this can be equal to e to the power of minus t multiplied by sine t. That can be found in the table. Just follow this general form in here. Okay, since that's the Laplace transformation for this term of the equation, then what is the y of t for this then? The y of t can be equal as a reversed shifting for that equation, h of t minus 3, which is a in here, multiplied by e to the power of t minus 3 multiplied by sine. Instead of sine t, we will have sine the t minus 3 to compensate the shifting. And this is the final solution for the Laplace transformation of an example where you have one term of the equation including a delta function transformation.